Good morning, everyone. My name is Patricia Porcel, and it's a pleasure for me to be able to talk to you about this research. It is titled Characterization of Cracks in Historical Buildings Using Image Processing Techniques, and this was a part of my undergraduate thesis. For this work, my supervisors are Benjamín Castañeda and Rafael Aguilar. The outline of this presentation in the first part will be the motivation, then I will explain the methodology and its results, and finally we'll talk about the conclusions and future work. The main motivation for this research was the development of non-destructive testing tools. This is because the characterization of anomalies is a significant contribution to the structural diagnosis process. However, most of the techniques currently used do not take into consideration the damage or the damage to the integrity of the material and the buildings. So the idea is to start exploring new testing tools that preserve that integrity. So another motivation for this research was also that this process of crack characterization is manual and it takes time. There is equipment that is able to detect the crack and do the image correlation to be able to get the area and the width. However, it is expensive and it's mostly really big, so it's not easily transported to different places. So if you want to be able to assess a lot of places, it's a very complicated procedure. And the third motivation for this research was also that in Peru, most of the heritage buildings are composed of historical buildings and churches, and these are mostly made of stone, adobe, or a mixture of both. And also, in the present architecture, 30% of the dwellings in the country, in Peru, are mostly made of adobe because of its low cost. For the methodology of this research, the first part is composed of the framework of the work, which is developed within the vision machine techniques. This technique and this framework is structured with these four elements. The first one is the tested structure, that in this case does include a target, an image acquisition device, which in this case we will use a digital camera, a computer to be able to process all these images. In this case, we'll use a workstation, and an image processing tool. This image processing tool is normally just an algorithm that can be based in different types of programming languages, and they basically responded to a necessity of this processing of the images. For this specific tool, we developed it in MATLAB, using MATLAB, and its image processing and computer vision toolboxes. For the development of the image processing tool, this work was based on the tensor voting method. This method allows each pixel to communicate with a predefined tensor field, meaning it can communicate with a vicinity of the pixels around it and decide if they, as a bunch, are within a border or not, and inside that border, if they belong to a crack or they don't belong to a crack. So this method is used to finally detect the borders of the cracks and allows the pixels to vote in a binary fashion, saying if they belong or they don't belong to a crack. For this research, we also designed a target that was used to acquire a precise data of the measurements of the crack, meaning this target allowed us to correlate its known measurements to the measurements of the pixels in a crack. With this data, we were able to get the area and the width and height of the crack. This target was designed with the red center because it allowed us to easily remove or separate it with the RGB layers. Finally, this target was also printed and positioned parallel to the surface of the crack. This algorithm is made so that the whole process is automatic. However, in the start of the processing of the images, after the user has gone through the monitoring process and take all the pictures, these pictures are an input for this algorithm, as well as these three numeric and selection inputs. So we have three user inputs at the start of the processing that are the measurement of the radius of the red circle on the target in millimeters, an ROI of the position of the target for a faster detection, a maximum and minimum approximate crack width. This is really important. The minimum is normally set to 0. If we have some anomalies or some things that might produce errors in the detection, we can rule it out with this minimum width. This is input also in millimeters because the target allows us to get that correlation of measurements. And the maximum is also used for the same purpose, to rule out anomalies such as markers or maybe even tubes. So this is a really important step. After that, the program runs automatically and we get three outputs. First, a log of all of the frames of the monitoring process in black and white segment with the segmented crack, an RGB photo with a green alpha outline of the crack as well for all of the frames in the monitoring process, and finally a file with the measurements of the cracks through the time of the monitoring process as well. In this file we get the height, the width, and also the area. We will now talk about the results, and we will see two case studies where this research was validated. The first study was the laboratory earthen samples that were subjected to uniaxial compression tests. And finally, we will see a case study with the 16th century stone masonry church of the Society of Jesus located in the main square of Cusco in Peru. The first validation process started with the laboratory earthen samples. These samples were created with cubic moles of 50 millimeters per side. The adobe composition was 60% of earth and 40% of sand. Then, after this mixture was combined, 10 to 20% of water was used to incorporate it. We got a paste that was put into the cubic moles and then dried in an oven for 24 hours at 65 degrees. And then these cubes, after they were dry, we positioned them in the compression machine, which was an MTS shown in the picture. And these cubes had to be at least 24 hours in room temperature before the compression tests. We also were able to position a camera with a tripod in a parallel position to get the images as parallel as possible to the cubes. And finally, this process was automated with an Arduino and a shutter cable. The quantitative results of this validation were provided by the IOU, which is the intersection over union, which was possible after the development of a ground truth framework. This was developed using 4 frames of the whole monitoring process of each of these specimens. So the first frame corresponds to the start point where there should not be any cracks. The fourth frame corresponds to the last frame of the process, and the second one corresponds to a 33% of the time of the whole process, and the third at 66. This was made because not all of the specimens finish at the same time, because the integrity of the structure might be different for each one of them. So we can also see in this figure, in figure 10, that, for example, for the first frame, where there should not be any cracks. In the specimen 4, we see a percentage. This means that in this specific specimen frame, we did have an initial crack. However, this crack was really, really small, and it was not fully detected by this tool. However, when we started to go further into the monitoring process of each specimen, we can see that the tool is able to recognize up to 92% of the crack in the last frame. This program has as an output the variation of the area of the cracks through an Excel file. And we are able, with that data, to get these types of graphs where we can see how the area of the crack has increased and decreased through time. For example, for specimens 1 and 2, we can get an accurate representation of where the point of rupture was and when the integrity of the specimen starts to drastically change. We can see in points C and G that the constant growth of the crack starts to change rapidly to get to that rupture point. This is also interesting because we can correlate this with the compression test, how the force of the machine starts to increase and decrease according to the resistance of the cube. The second validation was made with the facade of the Church of the Society of Jesus. This validation was possible because of a project for the structural health assessment of this church that allowed us to get these types of pictures of the facade. However, for this validation, we did not get a monitoring test, and because of its fragile state, we were not able to get the target on the facade as well. So for this validation process, we will only validate the segmentation process of the tool. This process was also validated with a ground truth, producing the result that we see in figure 13. We can see in figure 13 D, E, and F that the blue parts are the false positives and the red parts are the false negatives. The green parts are the parts where the crack was detected correctly. So we can see also the qualitative results in figure 14 that correlate to each one of the samples. So we can see that for this validation, the result shows that in low contrast environments, the tool does not correctly identify the whole crack. However, it does do pretty well, more than over 50% of the cracks above its resolution limitation. We can see that the results of this research show that this tool is able to segment correctly the cracks. It can also perform a geometric characterization of the cracks area through the time of the monitoring process. And however, because of this method relies on the image acquisition device, in this case it's a high resolution digital camera. This component makes it susceptible to illumination variations and also the changes in contrast. So for the future work, we propose that this research could be improved to target these types of environment with less dynamic contrast between the crack and the background. That's all. Thank you so much.